Here we go. I think that should be better for everybody. All right, cool. So I am here to talk to you a bit about some of the work that I am doing in the intersection of causal inference and predictive modeling, primarily with applications of healthcare. And I wanted to start the talk with a story. And this is a story about my very first research project. So in my very first research project, I was tasked with predicting mortality from Medicare insurance claims. So it's a big data set. And I figured I was straight out of undergrad, and I was very optimistic and hopeful about the promise of machine learning. So I figured, okay, I will take the Medicare claims that I have and I will put them through some machine learning model, random forest, deep model, whatever, and that will give me a good predictor for mortality. And lo and behold, it happened. I tested my model on a held out test set from the same distribution as the training distribution. And what I found is that the accuracy was great. I was able to predict mortality with a high accuracy. But the weird thing about this is that my models, all of them, kept implying that hypertension is protective against mortality, which you don't need to be a clinician to know that this is kind of an odd thing to happen. But hey, my model was doing well, and that's all I needed, so I kind of moved on with life. But then came time for us to apply our model to a slightly different distribution. This time it wasn't a Medicare distribution. So Medicare is for older adults in the US. This time we were applying it to a younger, less sick population. And once I did that, immediately the accuracy of my model deteriorated. So what was happening here? What was happening is that when clinicians file claims to get reimbursed by the insurance, by Medicare, the number of ailments or diseases that they can put into their claim was limited. So you had, let's say, 5 different diseases that you could write up in the claim to get reimbursed. And what happened is, for really sick patients who tended to die closely or die shortly after filing this claim, these patients, their claim slots were filled with things like stroke, dementia, cancer, end-stage renal disease. But for patients who were less sick, there was enough space on the claim to enter hypertension. So what the model ended up picking up on is that in this data set, hypertension and living a long life were correlated. The model was encoding an artifact that was only true in this data set. We see similar examples in the imaging world where you see models are picking up on artifacts like how a hospital codes left and right notation in the chest x-ray, for example, when we're trying to predict different diseases like, say, pneumonia. We see it in other applications. For example, in this work, they were trying to predict which skin lesions were malignant or not. And what ended up happening is that the model was giving a high prediction for a specific skin lesion, 0.59 in this example. And once you remove this little ruler or the scale that's on the image, the prediction or the probability of the skin lesion being, say, malignant dropped immediately to 0.39. And obviously, all of us as humans here can look at these examples and we can immediately identify what the failure is, and we can think of ways to mitigate it. But the reason why this failure mode was happening is because it was reflecting a paradigm that was and still is very common in machine learning, which is let the big data speak for itself. Let us, as much as possible, automate the process and not rely on human knowledge when we're trying to create these models. And this paradigm misses a really important opportunity for us to incorporate causal knowledge that we as humans have accumulated over decades and decades of experimentation and sort of gathering knowledge through different scientific disciplines. So a core question that I ask in my research is, and this is also the work that I'm excited to talk to you about today, is can we incorporate causal reasoning to build better models? What do I mean by better? There are three specific aspects that I'm at least going to talk about today. By better models, I mean more efficient models, meaning they require less data. Also, we can think of fairness. Better models might be more fairer models, if you want to think about it that way. And better models might be robust. So maybe we want them to be robust in distribution shifts, like the one that I showed in the previous examples. So whether we're shifting the age and the sickness of the population or removing artifacts such as the ruler from an image, these are all notions of kind of invariances that we want to be robust to. So what I'll talk about today is just two sets of work that I've done recently. In the first paper, or the first set of papers, we're going to talk about how can we create models that are efficient and robust when we know what the sampling bias is, or when we know what are the different artifacts that come from sampling. In the second set of work, we will look at efficiency and robustness to unknown sampling biases. What if I don't know what the sampling bias is? So jumping straight into it, in the first work, we will look at a specific example as a motivating example. In this example, we want to build a model to predict or to detect pneumonia. And at training time, we have images in their target labels, which indicate whether or not this patient had pneumonia. So the label Y is 1 if the patient had pneumonia and 0 if the patient didn't have pneumonia. We will also assume that we have the sex of the patient at training time. So we're not assuming that we have the sex of the patient at test time, but we're assuming that we have the sex of the patient at training time. And we'll call that auxiliary label V. So V is equal to 1 if the patient is a woman and 0 otherwise. And more specifically, we will consider a setting where we have bias sampling. So let's say that at training time, we don't observe many women with pneumonia. So for example, this could happen if women's pneumonia symptoms are less studied. So they go undetected for a while and the patient only shows up to the hospital when they're already in respiratory failure or have a lung abscess. So that ends up being their diagnosis rather than pneumonia. So in that example, you wouldn't observe many women with pneumonia in your training data. And let's, just for the sake of making things symmetrical, let's say that men who don't have pneumonia are also underrepresented. This is just out of convenience to keep notation clean, but this symmetry is not actually an assumption that we need for this work. Okay, so what we've seen a lot recently is that at test time, we're able to detect pneumonia among men, but not among women. And we'll say here that the model has learned a shortcut. And what I mean by that is that the model uses visual cues about the sex of the patient as a shortcut to predict the presence of pneumonia. And more generally, we define shortcut learning as relying on spurious correlations to predict the target label. We know women are not more or less likely to get pneumonia based on, like, say, biological reasons. We know that that is not a causal relationship. So the question that we're asking here is, can we build models that are robust to known shortcuts? And on brand, what we will do is we will look at this problem from a causal view. So what does it mean to look at this problem from a causal view or incorporate causal reasoning? We will start by codifying our knowledge about how the data is generated using a causal DAG. So that's sort of the language that we will use to codify the causal assumptions that we have. The DAG, I'm sure folks here know, but just to kind of give a quick one-sentence description, the DAG is a depiction of the causal relationship that we believe govern our observed data. So in this graph, the solid arrows encode a causal relationship between variables, or a possible causal relationship between variables, and shaded nodes mean that the variable is observed, while white nodes are unobserved. So I've already introduced Y, which is our target label in pneumonia, and V, which is our auxiliary label, which is the sex of the patient. X here is the X-ray pixels, and this X star, you can think of it as the visual cues signifying pneumonia. A little bit more formally, is X star is a sufficient statistic that summarizes the causal effect of Y on X. These causal relationships in the DAG are fixed, meaning it doesn't matter if I sample from hospital A or hospital B, these relationships will hold. But on the other hand, we have this dashed bidirectional arrow, which encodes that the two variables are correlated but not causally related. Instead of a dashed bidirectional arrow, you can think of this as there's a hidden common cause. It's the same thing. We're just simplifying the representation of the DAG a little bit using this dashed bidirectional arrow. So this dashed bidirectional arrow can vary between hospital to hospital. So if I sample from hospital A, I can have one type of correlation between Y and V, whereas if I sample from hospital B, it can be a different correlation. So for example, I can sample from hospital A, where the probability of observing a healthy woman rather than a woman with pneumonia is 0.9. But for hospital B, the correlation could be completely reversed. In fact, you can have the probability of a woman having pneumonia or observing a woman having pneumonia is 0.9 rather than 0.1. Okay, so the first nice thing about this causal view is that it gives us a concrete way to formulate the problem that we have and what we want. So we have, at training time, a data set that is sampled from some source distribution, and I'll use P with a subscript of S to denote the source distribution. And in the source distribution, there's some correlation between V and Y. So let's say that our data comes from the hospital where women with pneumonia are underrepresented. And we want some predictor F to predict pneumonia. So take us from X to Y. And we want this F to be accurate. But we don't know what our test distribution will look like. We don't know what kind of correlation will be encoded in our test distribution. So it can encode some correlation between V and Y that is different from the source distribution, but the causal relationships will be the same as the source distribution. So what we really want is we want this F to be accurate, and we want it to be robust to the shortcut, meaning we want it to have the same performance across all possible V and Y correlations. So that's sort of the first advantage, was to we can now explicitly state what kind of invariances we want. The second advantage of looking at this problem from a causal view is that it gives us a very concrete explanation for why shortcut learning is happening. So again, let's suppose that we're sampling from some source distribution where there is a correlation between V and Y. By looking at the causal DAG here on the slide, you can see that there are two ways that the information can flow between X and Y. So f of X is going to map us from X and Y. So if we look at this DAG, there are really two ways to get from X to Y. The first is the causal pathway, which encodes information about how Y causally affects the appearance of the X-ray. How am I getting that, or where am I getting that from? I'm getting that from the fact that this pathway passes through this X star, which is the causal effect of Y on X. Also, you can kind of glean that from the fact that the arrows are all pointing in the same direction. So that is a causal pathway. But there's another pathway that the information flows from X to Y, and that is the backdoor path. This backdoor path encodes information about V and the correlation between V and Y when trying to predict Y. So because of this backdoor path, whenever if I'm just running a naive deep neural network that predicts Y from X, what I will get is a conflation of those two paths. I might get some causal signal, but I also will get entangled with that. I will get some of the information from this backdoor path through the auxiliary label. So far, our causal view gave us two things. The first is we're able to kind of concretely define what is the set of invariances that we want, and we can explain why this shortcut learning happens. But the really nice thing about the causal view is that it will allow us to chart a solution towards this problem of shortcut learning. And I'll start with a population result or an asymptotic result. So what we found is that if you take this causal DAG that I showed you in the earlier slide and analyze its properties, you will find that there exists an ideal distribution. This is the distribution where there is no correlation between the sex and the patient of pneumonia. So this is a distribution where you're equally likely to observe a man or a woman with pneumonia. And if we are lucky enough to sample from this ideal distribution, and if our sample size goes to infinity, then our model will be independent to shortcuts. I just said two crazy things that should make you at least a little bit uncomfortable. One, if we sample from this ideal distribution where there is no correlation between Y and B, it might be really difficult to sample from this ideal distribution, especially in healthcare systems where there might be barriers to access of like high quality healthcare. The second crazy thing that I said is if our sample size tends to infinity, or for an infinitely large sample size. We never have the setting. We're always working with a finite sample, like a sample size of n or something like that. So in the next two slides, we'll look at what happens as I relax those two crazy statements, starting with the infinitely many data points assumption. So we're going to relax this assumption that we have infinitely many data points and look at how different models perform in a sort of a finite sample setting. So what we did is we looked at the efficiency. By efficiency here, I mean statistical efficiency. So how well does a model do with a small sample or a fixed sample? So we looked at the efficiency of models that conform to the causal DAG compared to the usual methods of training. And what we found is that the usual models, or the models that conform to the causal DAG, they tend to be more efficient than the usual models. What do I mean by the usual models? I mean models that are minimizing something like the prediction loss and some penalty to constrain the complexity of the function space, like an L2 regularizer or an L1 regularizer or dropout, or any of those tricks that we typically use to constrain the size of the function space. Okay, what do I mean by models that conform to the causal DAG? In contrast to the usual models, these are models that do not encode correlations between V and Y, and in doing that, they conform to the causal DAGs. In other words, these are models that give us predictions such that the distribution over the predictions for men is the same as the distribution over predictions for women. In practice, one way we can do this is by minimizing a suitable loss, but then penalizing the maximum mean discrepancy, or MMD. A very brief kind of walk through what the MMD is. The MMD is a way of measuring distance between two distributions. So if you're looking at those, the two plots on the one on the left-hand side, it looks like the two distributions are similar to each other. So they should get a lower MMD, whereas the one on the right-hand side, the two distributions look quite different. So they have a high MMD, they have a high distance. One way to intuitively understand what this MMD is doing is if you give me two distributions and you say compare the two distributions, the most straightforward way to do this is let's compare the means. Well, the two distributions can have the same mean, but different variances. So you can say, all right, I'll compare the mean and the variance. But you can play this game like, okay, fine, same mean, same variance, but they have different skewness or a different kurtosis. So instead of comparing moment by moment, what the MMD is doing is it is comparing infinitely many moments of the two distributions to figure out how far apart they are. That's sort of the brief intuitive way of thinking about this. You can also try to kind of enforce this kind of penalty using other other things like the KL divergence, like the Wasserstein distance. That is true. This just happened to give us the most elegant math, and it's also nice to have the symmetry, which the MMD has, but something like the KL divergence does not have. Okay, so this is the sort of upshot of what it means to have a model that conforms to the causal tag. And remember, we're still assuming that we're sampling from the ideal distribution. I wanted to quickly explain the intuition behind this proposition using a very simple example. In this example, we only have two variables. So X is no longer pixels of a chest X-ray. It's just two variables. The first one is the bad variable. It kind of encodes some information about the auxiliary label or the shortcut label. And the other is the good variable that sort of affects the value of Y, our main label. And the important thing to keep in mind here is that we don't assume that we know which is which. So I just observed two variables. I don't know which one of them is good and which one of them is bad. And what we want here is we're going to assume that the model is linear. Again, very, very simple setting, just to kind of highlight the intuition. And what we want to do is we want to find the optimal model. And to get an intuition of how we can do that, you can think of the problem of finding an optimal model similar to a search problem. I will define a search space and I will find the best model that fits my data. So the search space here is the function class. And I'll use this graph here to show different function classes. So what you're seeing here on the x-axis is the possible values for the weight or the coefficient that the bad variable takes. So these are the coefficients for, roughly speaking, the auxiliary label. And on the y-axis is the good coefficients. These are the coefficients that, or coefficients and or weights that get multiplied by the good variable. So in an ideal world, we would only consider or only search over the function space that's the straight line, because this straight line, it's good because it allows us, it sets WV values to be 0. And why is that good? Because if WV is not equal to 0, that means that the model is encoding some information about the shortcut. So if we decide to do something like L2 regularization, the function space that we would end up with would be this yellow circle. The yellow circle is far bigger than the ideal straight line that we would like to be searching over. And why is that a bad thing? It's a bad thing because, again, think of it as a search problem. It's a bad thing to be searching over a big space or a big function space for the same reason that it is bad to know, like it is better to know that I've lost my keys and they're somewhere in my apartment. It's way worse to know, okay, I lost my keys and they're somewhere in New York City. That is a far bigger search space, so it makes the problem harder. So it's always better to be searching over a smaller space. Okay, so how do models which conform to the causal tag do compared to the L2 regularization and the ideal distribution? It turns out that the causally motivated regularizer, or the MMD regularizer in that case, tends to squeeze that distribution by limiting how the values that WV can take without knowing which variable is the good variable and which variable is the bad variable. The only signal that the MMD is getting from the data is it's just getting the label of the auxiliary label. So in the paper, we make this argument a lot more formally, and we show that you can establish that the Rademacher complexity, which is a measure of the function, measure of the complexity of the function class, is smaller if you use this causally motivated regularizer. Okay, so to quickly recap, what we saw is if we're sampling from the ideal distribution and our sample size goes to infinity, we get robustness to the shortcut. And even if our sample size doesn't go to infinity, we get statistical efficiency if our model conforms to the causal tag. Now, what happens if we sample from an arbitrary distribution, not the ideal distribution? Unfortunately, neither of those two results hold. So what are we going to do about this? Very conveniently, this is a problem that we've thought, sampling from a non-ideal distribution is a problem that we've thought about a lot in causal inference. So again, we turned to causal inference to address this issue. In causality, we often have a notion of the ideal distribution, which is the distribution of a randomized control trial where there are no confounders confounding the relationship between the treatment and the outcome. And we often reweight the data to mimic the independencies that exist in a randomized control trial. So we did something similar here, where we used weighting to map us onto a distribution that looks like the ideal distribution. And this helps us recover independencies in the ideal data or the ideal distribution. If you stare at those weights for a second, you'll realize it's very simply the Radon-Nikodym derivative of the ideal distribution with respect to the observed distribution. Okay, so how does this translate into an optimization objective? Our objective will be to minimize a weighted logistic loss or a weighted suitable loss and a weighted penalty term. The second penalty term penalizes models that encode information about the sex of the patient, which is that MMD we talked about earlier. But importantly, both terms are weighted using the weights from the previous slide. And alpha here is a hyperparameter that you can pick through cross-validation. Okay, so remember that our causal perspective helped us design those weights, which allows us to statistically manipulate the data such that it looks like it's coming from the ideal distribution. And also our causal perspective allows us to design this weighted invariance penalty that encourages the model to encode desirable independencies. So one quick comment I wanted to say before moving on to empirical results is that if you take this objective function and you try to find the value of alpha using the normal cross-validation methods, you might end up in a way, so normal cross-validation meaning you're looking at the held out validation set to find the model that gives you the best accuracy. A problem that you might end up with here is that this alpha, if you're picking it in this way, just looking at the best performing model on the validation set, you might end up in a situation where you're consistently picking very small alphas and not regularizing that shortcut at all, because the best performing model in distribution might still be the one that leverages the shortcut. If there's any information in the shortcut, it is better to leverage that information to get like the highest possible accuracy. So instead of doing that, what we did is we designed a cross-validation procedure where for each value of alpha, we treat it as a hypothesis test. We're going to test if the corresponding MMD in the held out set is statistically significantly different from 0. If it is not different from 0, that means that our model is successful somewhat in regularizing out the shortcut. So for all values of alpha that give us an MMD on the validation set roughly equal to 0, from that subset, we pick the best performing model. So step 1 is akin to saying, I'm going to check which of my hyperparameters give me invariance. And then the second step is akin to saying, all right, of the ones that give me invariance, which are the ones that perform best or have the highest accuracy? Okay, so how does this translate into empirical results? We wanted a data set where we can control the correlation between Y and V at training and test time. So instead of using natural images, we used simulated data. And our task here is to predict whether the bird in the picture is a land or water bird. So that's the main label. And the auxiliary label is the type of background. So it's either land or water. And similar to a couple of other authors, we followed a similar setting where we simulated data by taking images of land or water birds and superimpose them on land or water backgrounds, as you see on the slide. And this allowed us to simulate a training data or a training setting where the majority of water birds are on water backgrounds and land birds are on land backgrounds. And the way we're going to evaluate whether or not our model is relying on shortcuts is by testing it on many different test distributions that encode different levels of spurious correlations between B and Y. And a model that doesn't rely on the shortcut will be sort of invariant. It will have the same performance across all simulated test sets. So looking at the results, we have on the x-axis the correlation between the background label and the main label at test time. And on the y-axis, we have the AURC at test time. And this dashed line that you see on the slide is the line, it depicts where the training data was sampled from. So at training time, the probability of land bird on land background was about 0.9. Okay, so we will compare our model, which is the orange model, to a typical deep neural network. In the paper, we compare to a number of other comparisons like distribution robust optimization models and things like that. So if you're interested in more, please check out the paper. But just to keep it simple, we'll focus our analysis on those two comparisons. So what we see is that our approach has a better AURC at every target or test distribution. And this means that our model is less prone to relying on non-causal factors in its prediction, which makes it more reliable than typical training methods. But before declaring victory, let's look at what happens if we drop either of the two components in our suggested approach. So the gray line here shows a model that uses our weighting scheme, but not the invariance penalty. And it is doing a little bit better than the typical deep neural network, especially when you look at the sort of like most shifted distributions, but it's not quite at the level of our main approach because the function space defined by this model is not regularized by the MMD. So there's a loss of efficiency there. And the green line here is applying the invariance penalty on the observed distribution without reweighting. And yes, it is doing relatively well in the extremely shifted populations, but it is terrible everywhere else. And this line actually it's similar to very commonly used approaches that have been suggested in recent literature. So invariant risk minimization, or REX, are two examples of these variants that end up being overly conservative in regularizing the model. Okay, some empirical results on a realer data set, which is we'll look at in the context of predicting pneumonia. So we used Checkspirt and downsampled women who do not have pneumonia at training time. Again, similar to previously studied setup. And the task here is to predict the onset of pneumonia, which is our main label, while making sure that sex is not used as a shortcut. Again, what we're going to look at is the accuracy of the prediction as measured by the AURC. And we're going to compare our approach to the typical deep neural network in two settings. One is where we train in one hospital and test on the same hospital, so there's no shift. And in the second setting, we're testing and training on two different hospitals, so there is a distribution shift. And what we see is that our approach actually does better in both settings. Is there a question, or do I need to stop for any reason?
No, go ahead, please.
Okay, cool. All right, okay. So what we see is that our approach does better in both settings, the shift and no shift. And it's not surprising. Well, it might at first come as a surprise to like, why are we doing better even when there is no shift? The reason why that's the case is because this causally motivated regularization gives us an improvement in efficiency, even independently of the shortcut reduction. So even in sample, we might sometimes get an improved efficiency, but that's not guaranteed. Okay, I wanted to very quickly talk about the relationship to fairness in the setting. So you can kind of restate a lot of the things that I said, and instead of a shortcut label, you can think of a sensitive attribute. And in a lot of cases, there are two properties of fairness that people typically look at, which is separation, that we want sort of like conditional on the main label. We want the prediction to be invariant to the sensitive attribute V, or we want it to be unconditionally invariant. I will present the relationship to fairness relatively quickly. But if someone's interested, I'm happy to sort of like chat offline. So by analyzing the causal DAG and thinking of its implications to fairness, what we found is that if you're sampling from an arbitrary source distribution PS, the optimal invariant F, meaning the robust predictor F, implies separation. So you will get this conditional invariance. But the optimal invariant F is at odds with the independence property. Very intuitively, without getting into details, the reason why robustness is at odds with independence here is because if you look at the causal DAG, without conditioning on Y, you still have those two active pathways that connect you from X to Y. So any biased distribution, the true data set has the two pathways. And if you are kind of requesting and demanding that f of x is independent to v unconditionally on y, you are going against the causal DAG, because in the true causal DAG, there is another causal pathway that you're kind of ignoring when you're requesting that kind of invariance. So that was one finding. Another finding is that we can expand the fairness toolbox a little bit, because what people have typically done when they are trying to get separation, so they're trying to get this conditional invariance, is you minimize the prediction loss and you minimize the conditional MMD as well. So you say conditional on y, so for every value of y, I want the MMD to be 0. So what we realized is that asymptotically, this the objective that you're seeing on the slide is equivalent to the marginal reweighted MMD that I showed you in the previous slides, which is you're minimizing the weighted loss and you're minimizing the weighted but marginal MMD. And you can show that those two losses are equivalent asymptotically. In finite samples, those two losses are not identical. They will have different advantages and disadvantages. So what you're looking at here is on the x-axis is the model. So there's the weighted marginal MMD and there's the conditional MMD penalty. And I'm showing you on the y-axis the estimated MMD and broken down by y is equal to 0 and y is equal to 1, and looking at the training, validation, and testing data set. So if you look at the weighted MMD, you'll see that it has good generalization in the sense that when the training weighted MMD is 0, the validation weighted MMD is 0, and the testing MMD is 0. Whereas for the conditional MMD, the training MMD can be close to 0, but the validation and testing are high. So it's kind of pointing to a notion that maybe we're overfitting the MMD penalty itself when we do the slicing. And that's sort of not very surprising because the MMD is an estimated penalty. It's not like the L2 where it's just you're computing the norm. No, you are estimating a distance between two distributions. So when we slice the data set based on y, you are effectively reducing the power of the data set that you have in order to estimate the MMD. So that is one reason why the weighted MMD, weighted marginal MMD might be better. Of course, weighting also increases variance. So one practical takeaway here is to look at the validation set MMD and see how well it's comparing, or how similar is it to the training set MMD. And if you see that the two are very different, then that means whatever method you're using might be overfitting or might have high variance. So that wraps up the first part about the sort of the invariance penalties when we know what the shortcut is and their fairness applications or their fairness repercussions. The second and last part of the talk, I will quickly go over, well, what happens if I don't know that sex of the patient is the shortcut? And that's sort of a very reasonable question to ask here, is that how often does that assumption actually apply in practice? So what we have in this setting is a large number of candidate auxiliary labels. So with every X-ray, we not only have the patient's sex, but also the type of X-ray machine, and maybe other medical conditions, for example, whether or not a person has the flu or edema or different types of cancer. And we don't know which ones can be shortcuts or which ones are shortcuts. And still, our ultimate objective is to develop a model that is robust to here possibly multiple shortcuts. So if you recall, this was our causal DAG that we discussed in the first part of the talk, where we have that Y causes X star, which ultimately affects the inputs X. And we will keep that assumption, but we will relax the assumption that we have only one V. And this will allow us to consider a class of DAGs where the additional auxiliary labels could be one of many things. So this class of DAGs has a high dimensional auxiliary label set of labels VD, and I'm using the superscript D to tell us that we're no longer considering one V, but rather a vector of length D. And we will limit the set of auxiliary labels a little bit by saying that it can either be VP, which are variables that are correlated but not causally related to Y, and they are causes of X. And we have V complement, which I will denote with VC. And these are any other variables as long as they're not caused by X. So we're kind of assuming that we don't have any variables in the shortcut set or possible shortcut set that are caused by X. And some of the examples of this kind of causal DAGs is that we can have V complement is the parents of the target label, such as the flu, which causes pneumonia but does not directly appear on a chest X-ray. Or V complement could be variables that are correlated with sex, such as socioeconomic status indicators. And important to keep in mind here is that we're not assuming that we know which is V and which is VC. But we still want some f of X that is robust to any changes in correlations. One naive solution would be to develop a model that induces independence to all VD. So again, we define weights similar to before, and we would try to minimize this with this penalty, additional penalty in the second line. Turns out that the MMD doesn't quite work, but you can trivially kind of extend it to the Hilbert-Schmidt independence criterion, or HSIC, which you can think of as an extension of the MMD that allows for arbitrary types of VD, arbitrary types of auxiliary labels. So they can be continuous, binary, whatever, and they can be of arbitrarily high dimension. So the problem with this is that the HSIC, this penalty, its accuracy deteriorates as the dimension of VD increases. So as VD increases, you might get the penalty telling you, oh, well, you have no correlation between your predictions and the auxiliary labels, when in fact, you do have a correlation. So it can be misleading. So ideally, we want robustness penalties that are defined with respect to a small set of sufficient auxiliary labels. Similar to the first part of the talk, we started by analyzing the set of causal DAGs, and that helped us realize that you can provably show that invariance with respect to VP only is necessary to induce robustness against any correlations in this system. And this finding would be helpful only if we're able to identify which is VP and which is VC. And the good news is that we also found that this VP is identifiable through two sets of independence tests. I'll kind of skip the details of those two independence tests because of time, but the upshot is there are two sets of tests that you can conduct on your auxiliary labels, and they will give you an answer to which is, they will help us identify which is the kind of the sufficient set of auxiliary labels that we want to be invariant to. So I'll skip over that part in the interest of time, but I'm happy to chat with folks offline. Okay, so that gives us a new training procedure where in the first step, we conduct those two independence tests, or those two tests that I didn't quite go over, to help us identify a sufficient set of shortcuts, this VP. And in step 2, we will kind of follow a similar template to the first part of the talk, where we reweight the data, only taking into consideration VP as the shortcuts, and then optimize using the Hilbert-Schmidt independence criterion, again with this reweighted penalty and the reweighted loss. So revisiting the water birds experiment, our objective here is still to predict the type of bird, but now we have a high dimensional set of auxiliary labels. Only 2 of them are sufficient or relevant. And so here VD has a dimension of 12, and VP is only 2 variables. So the 2 relevant shortcuts here are the background and the camera quality, or like noise artifacts of the camera. And the images that I have on the slide are like, you have a water bird on water background, you have a water bird on land background, and you have a water bird on land background with some noisy camera artifacts. And these are just like the black blobs that are on the image. At training time, most of the water birds are on water backgrounds taken with a good quality camera, and the opposite is true for the land birds. And again, we tested on varying distributions. So on the x-axis here, we'll see that this is what the test distribution is. So on the right-hand side, the test distribution is the same as the training distribution, but on the left-hand side, they are diametrically opposite. So the similarity decreases as you move to the left-hand side of the plot. And on the y-axis, we still have the AURC at test time. And we look at the usual way of training deep neural networks. That's the black model. And we'll also look at a naive model, which tries to induce independence to the full set of all the auxiliary labels, so all 12 auxiliary labels with a dimension VD. And finally, our approach, which instead of building invariance to the whole set, what it's going to do is first attempt to identify the sufficient set VP, and then introduce or try to induce independence to it. And what we find is that our approach outperforms both models, especially when the test and training distributions are very, very different. So that sort of wraps things up. And just to recap, we looked at what happens, or how can we build invariances using ideas from causality when we know what the shortcuts are, and what we know when we don't know what the shortcuts are, and some implications with respect to fairness. I am very happy to take questions. I see there are a couple in chat, I think.
Yeah, thank you very much, Maggie.
Yeah, sure thing.